Try to get that work. There we go. Okay, good. So I'm going to talk about what I like in driverless. Moves pretty fast to get the 20 minutes, and hopefully we can get a question in there. So I'm going to go talk through this. So I'm going to take two recent problems that I've done. I'm going to take my approach while I looked at the data before driverless came in, and then how I looked at it with driverless. So we're going to talk a little bit. I'll show you what the problem is, a little bit talk about what the data set was. We'll start with my approach, and then in both cases we'll talk about what the driverless created, a couple different feature types, and then actually whether those models were good or not, in addition to what the features are. This is feature rich, but we want the models to work as well. So who am I? As Len says, data scientist at H2O for about 2.5 years. Used it for about another 6-9 months beforehand. Done a lot of Kaggle competitions, as most of us have in this little block here. An R user, H2O, data table, GBM, those are my main tools. But most importantly, I'm the driver for this sort of thing. So the person we're comparing how well driverless works. So the first problem we'll look at, how many attempts will a student make? So we have, the data is an online question and answer platform with computer science problems. And the goal here is to predict the number of attempts a particular student will make on a particular problem. So we have a student ID, a problem ID. We're going to try to figure out how many times they attempted that. Next slide will show us kind of how that is framed up. So the additional data on that for the student, we don't have a lot of features. I think it works out about 17 features for this one. So student, we have level, that's an important one. So it's sort of beginner, intermediate, advanced sort of thing. Our ranking, this is a number, generally higher is better. And the highest ranking these students achieved. A couple more things too, but those are the key ones. And for the problems, we have what type of a problem is, a couple of different genres of computer science problems, 3-tier level, another one, hard, medium, and how many points were awarded to the actual platform when someone got it right. So we have about 124,000 rows, so it's medium data, we'll call it, but good enough to find a signal. A lot of testing data, so we should be pretty accurate. This was framed, it's a regression, how many times will someone count it, but it was framed up by the end user that they wanted just bucketed. So we've got, you see on the right-hand side, 1 through 6, and they have a couple different numbers, and we cap out at 10. And on the left side, kind of backwards a little bit, you have the volume. So it's very heavy in 1. Most people try one problem. Perhaps they get it right, perhaps they get it wrong and don't come back. But over half of our volume is in that 1, and so we're going to try to separate the signal really from the next couple. It actually grows a tiny bit at 6, and that's interesting because where we see the models go. So here we go. What did I do? I look at this problem, and it looks to me, I pigeonhole it in a recommender problem. This is, recommendations usually what you want to provide. Here, it's a little more like the Netflix star rating, Yelp rating, something like that. But really, I see this as a 2D problem. I have, instead of users and items, here I have users and problems. And so I'm thinking, I'm just going to go to that genre of what we're doing. And those tend to be, so standard would be matrix factorization, libfm, things like that, collaborative filtering tools, whatever your favorite sort of stuff is. My favorite is still GBM. So you're using deep categorical encoding. So you can use a GBM to do these things. You just kind of have to work hard at it. But also, a lot of what I'd like to do when getting going is sort of get a feel for what the problem is. This is a data set that wasn't familiar to me. And so I sort of tend to probe it a little bit. That little table at the bottom is something, this is part of a paper I kind of produced at the end of the road. But showing that if you just use, we only have, again, about 17 features. And I'm really trying to see with each dimension, how does this play out if I just use these in isolation? Doesn't always help me in modeling, but it helps me understand the problem. And so this is almost ordered top to bottom. F1, you want that to be higher. So, and it's a multinomial, so an F1 under 0.5 is okay. So the rank of the user, not very useful. That's good to know. The user itself, if we just memorize the user IDs, we see them enough that that's reasonable, but it's not all that good either, and that kind of surprised me. I actually figured that, let's find the good students. They're going to just do really well on these problems. But quickly what you realize is the problem itself is actually second to last, and there's some interactions in there. So I tried a lot of the 1Ds and then put things together. It's kind of manageable at this number of columns. To try to combine things and see how well that does in isolation. And that really, this is really like a poor man's target encoding that we use in driverless. So it's not surprising that we will see these come up a little bit. Doing this in R is not entirely fun. So there's a couple of these. It winds up this messy chain of code. Because actually I put in a hierarchical sort of way of doing this too, because I know the hierarchies. I know this data set well enough. I get used to it. So at the bottom you have these crazy if-elses, and I feel bad when I write them, but I can't get away from them. These are 2 of these, but my code has a whole bunch of these blocks in there. So try to feel that out, throw it in, my favorite, the GBM, and we see in the top 3 here are using those deep target encodings. This is actually aligned pretty well with that F1 chart you saw before. And even below that, we start to see some of the other ways of almost the exhaust data of a target encoding is how many times you see that. It's more the frequency. So the top 7 or 8 variables are all that. It's all taking these target encodings, all this. Let's figure out statistics of how often we've seen this person, how often they do this type of problem correctly. The first natural feature we finally found down there is that max rating, and that's worthy of mention because we'll also see Driverless find that. So that's roughly what I did, and now let's see what Driverless did. I completed this problem first. It took me a little while to get my NVIDIA Docker set up, so this is sort of in retrospect. I tried it. So here we go. I put these in anyway. But the main feature for me is that thing in the middle on the bottom. So this talk will be about the variable importance. That's kind of what I pay attention to when I do regular modeling. That's why that chart was up here. That's what I pay attention to when I watch the driverless. I think it's cool when it moves around because I usually do work off on a laptop, and this is my workstation working for hours away, and then I just pay attention whenever I see it shuffle around. Because I'm kind of watching how it moves over time. I'm very curious about that. Hopefully we can get some importance out of that. Here's the chart, but I'll break these top ones down in more detail. So these are the top 5 that Driverless found. And let's jump into those. So the top one, 16, I find that number interesting because you see reuse of some of these features, especially for this. It's a multinomial target. This actual feature, so this is the target encoding of the problem ID. We see it used many times because at the very end, that 0, this is the probability of class 0, which on that previous chart we saw was 53%. So it's not surprising that it's going to try to figure out whether yes or no almost. It turns into a binary when we look at it this way. The probability of the problem ID being a 0. And this is using cross-validated target encoding. That cheap little R code I had was not doing cross-validated target encoding. It was legal. It's just a method that you wind up having to do a couple little shortcuts to get it to work efficiently. But here, I just know I have reasonable cross-validated target encoding. That's really powerful. It's a powerful weapon, and you can use it for bad if you don't know what you're doing. So Dimitri's put a lot of good effort into making sure that this thing that could be dangerous is actually really helpful. That's why we see this used a lot. If we move into the next one, we have a target encoding again. But now it starts to do interactions. So the first one was just problem ID on its own, which we already kind of knew that was really high in the regular F1 ranking. Now we're interacting points times problem ID. And so the first one, I'm happy that I see it because I knew it was there. Problem ID was shown to be pretty good, so it found that. I'm happy. I don't want to miss that. Here, this is interesting because I didn't actually find this. I didn't even try. I didn't see this coming. I thought problem ID was the root level, the key, if you will, in database structure of every problem, but it isn't. It turns out they can offer different points for that problem in different settings. And to be honest, I don't know the nature of it. I didn't see it, but Driverless found that was interesting. So whether it offers points or the different level of points, if you look at that allows you to subdivide the problem ID a little bit, which is ultimately what I want to do. All those interactions are subdividing everything as deep as you really can because with enough volume, that's still a powerful way to do things. So I'm already pretty interested at this point because it caught something I didn't catch. Max rating, that's not very interesting, but it was the same thing that we saw in the GBM. That was the top natural feature. So it's used as is. It has a decent distribution, so I didn't find a different encoding for this one. Here we have another semi-exotic sort of thing. This is really, we saw a lot of the denominator features in there. I don't know if you caught it or not, but that's what we're saying the exhaust data from the target encoding is that you counted up how many times you saw something. That's what it's doing here, but it's doing it with interaction. And both of these, last online time seconds and rating, I actually played with a lot of different encoding schemes for these. I tried to get more out of it. Particularly in the last online time, because I played with rankings and just different distributions, different ways to bucket things, and I never got anything to really do any better than just using it naturally. But I didn't try it in interactions. And that's the thing, it's exhaustive, and so it's trying many things that I didn't necessarily think to try. So again, the frequency is it's counting up how many times it saw that interaction. Here, num to cat target encoding roughly is just a target encoding. It's just that we've binned something, and we're going to then treat it like a categorical. So, and here we have a 4-way interaction. I just wasn't going to try that. So that's rating, max rating, points, last online time. So the points gets us in the the problem space. The other ones, I believe, are all in the user space. So this is our first actual combination of those two entities. That's the only thing I find surprising a little bit, that it didn't, in the top, find more things that are interacting those two dimensions that do play together. But we do have that captured here. And the problem ID, even if you look at that original F1, there wasn't a big difference between problem ID and then interacting that with the user. And you have to do it only with the user level. If you've never seen a user do that problem before. So this is pretty interesting. I mean, this is definitely an example of something I just would never have really thought to try. But it did, and I found it was useful. And there's a difference when I was saying that. So did I try them? 2 out of 5, yes. 3 out of 5, no. So a quick run through again, and if we look a little further, we see a lot more target encodings too, so that's actually kind of familiar. I pulled out the top 5, but we see, I think it's 4 more target encodings down there and 3 more num to categorical target encodings. And ultimately, that's all my model really was. I had a lot of these different shapes and rankings and all sorts of ways I was trying to move the numbers around. All that I was really left with was a lot of those target encodings myself. So Driverless is pretty much doing what I'm doing. It's just doing it a little more exhaustively. Moving on to the second problem, we have bank customer churn. This isn't entirely a churn definition you might be familiar with, but this is the way it was set up. So we have customers likely to churn their balances in the next quarter by 50%. So they're not leaving us entirely, but similar type setups, churn problem in its heart. Even more data, we have 300,000 to train with, 377 columns. That's an interesting number. That's a lot. There's plenty more, certainly, but 377 is a lot to digest, especially when you're looking at one new. For the data set, what else do we have? Pretty slim. It's mostly the monthly balance history. So customer, age, enter demographics, a few other basic things, reported assets and liabilities when they applied, it looked like when they set up the account. And then a lot of things about monthly balance history, different financial bits that they can do of their activity. And they're doing that with multiple things. We'll see that they have already pivoted these, lagged them by month. So what did I do? Title this one Exploit Before Explore. So explore, exploit, this is all the way of how you iterate through these things. What are you doing and how are you refining this feature space? There's a big deal with reinforcement learning. But in the manual mode, I typically tend to analyze the data sets first, kind of come up with some hypotheses and then model and then go from there and then iterate that. But with 377 columns and wanting to go a little fast, I just flipped it a little bit. So here, I use the GBM to tell me where to look. Go exploit that, and then I'll investigate more. I'll explore about these. So what that GBM up there does, we've got 2 kind of bulky things, this recency of transaction, final worth, and then a bunch of lag features. And so I didn't actually know that. I hadn't looked at this much originally. So I just let the model do the thinking. So I see that. I see these lagged features, and I think, okay, I know what my next action is. And I say that more specifically, so we've got balance previous 1, balance previous 5. It turns out I think it's 1 through 6, something like that. So the immediate reaction to that, you just see that, you spot it, we're going to do some math. So we're going to start subtracting features, dividing maybe, and so trying different, in fact, that's where we actually do. So jumped ahead a little bit. Because the raw balance is interesting. We don't want to throw it away necessarily, but it's not as interesting as what's that customer doing over time? Are they already pulling out their balance? Did they move from 500,000 to 200,000? Or do they move from 5,000 to 6,000? One balance is much bigger than the other in those cases, but one person's pulling out their money. That's the action that at least we're going to try. I don't know whether that's correlated to what we're after here, but I certainly think that's a good thing we can try. And I know that decision trees have really trouble seeing this. The way they're going to build their interactions can technically capture this, but if presenting these relationships to them in a more natural way is always a good idea. So here we go. That's kind of what I did. So what did I do? I calculated some of these. With the exploit step, I pulled off the top 2 things, or actually top 1, I think, that was coming back from the GBM, and I focused on that. Created some really quick functions here to calculate those diffs. It looks like the rates as well. I tried one field. We have a dozen more of these, but that's just me. I tried one, I worked with that, I saw what was happening. I did try another model and went through that, but what driverless did got me to stop pretty quickly. So this time I had driverless ready to go, so I'm doing all this, and driverless is ready, I just hit the button. Again, here's the variable importance list, and it was way better than wherever I was going to go very quickly. So on the left, driverless can do math. So it doesn't know that this was a good idea for this problem. I knew that, but it figured it out. So it's fairly smart. What it's doing is it tries these things, but the way that we're capturing from a tree model what the tree model liked and what was working, really it's producing some really interesting results to me that I find quite engaging. So the first one is that it's an interaction, because that's really what it is. It's actually subtracting some things I didn't try, two different variables. So calculating some differences. We see it again, down there, maybe 5 and 7. If we break apart, we find a lot of diversity in this list as well. So there's 3 subtraction features just in that top list of top 14. There's a truncated SVD components at number 2. Well, I'm going to try that. I mean, I've used that before, but it takes a while. It takes me to really feel like I need some compression going on. Text features, really wide, sparse data. I would not have felt that this was normal. Cluster distances. Sometimes I'll try this. Talking with Dimitri and working with Dimitri and Brandon, they both said that they actually do try this a lot more, so I've tried to get in the habit of doing cluster distances. But something that's interesting, I almost need to go back to show this, is that normally what would I do? I'll throw it all in the cluster. Why not? It's 377 things. I have nothing better to do. But driverless is doing subsets of these. 4, 6, 8 columns. I can't say those are the best 4, 6, 8, but it's probably better than 377 all at once into something with a lot of assumptions about the model. So it's kind of interesting in that what it'll try. It's trying things that I probably would have never tried, and if I had, I probably would have learned very differently. So again, we have a target encoding one in this one, but that's interesting. 2 flavors of problems. We had heavy target encoding in the last one, just 1 out of the top 14 here, and that makes sense. There's a lot of math going on with this one, and 3 direct features. Here's getting ahead of myself again. So yeah, the cluster one. So we see we've got 4 variables coming into the cluster, 3 going to the SVD, and 2 of them are even the same, that D previous 1 and 2. Maybe it's a different way to do some of this math. These are linear equations at the end of the day. So it's just coming up with really different encoding schemes to try to capture the information in that data set. On the first iteration, like if you watch this thing move 40, 50, 500 of these things, like on the very first model, it was far beyond my intro model. So I gave up. So I just watched this thing work. I tried a couple different variations of driverless at this point. And this is something, I don't know that we've said this enough. Dimitri probably did a couple times ago, but the accuracy was stable. I've noticed this with my models. I would say that there's a problem where driverless wasn't really doing what I could do out of the box, but that was stable, and these are stable too. So these exotic features, they may seem unstable, but I think we've worked hard to put descriptions in there that tell you what we're doing, and go to the docs. Like if reading that description doesn't tell you what you need to know, if target encoding is a foreign concept to you, don't take that lightly. Our docs will walk you through a little amount of that more, and hopefully in the future we can even send you one more deep, level deeper to give you like a 3-5 page white paper on some of these things, because I think that's what a lot of you, I think, are in talking to you are going to kind of want. You want to understand what this is doing. I like it. I get what it's doing. I've seen these transformations for years. Don't always use them, but I know what they are. But we don't expect you to. A lot of people, this is really engaging because you don't have to use them. You don't have to know how to use it. But most people want to feel comfortable with what it's up to. The last one is a computation problem. So we do have here is Analytics Video, who's hosting our hackathon right now, actually. So there's me tied for 5th by literally just pressing the driverless button. I didn't even use my model whatsoever. I hit it a couple times and I averaged them together. That's kind of an interesting way to explore. I don't know if we get a recipe in there that helps you do that. We don't really want you to hit the button 20 times and hope for the best. But what I like to see is that I've teamed up with the guy in 3rd there, SRK, many times, most in Kaggle. He's a Kaggle grandmaster, so got beat by him by just a little bit, but I beat a very good Kaggle grandmaster just below. Rohan's a really good feature engineer, actually. I've worked with him a couple times, and in 8th position was someone who reached out to me on LinkedIn saying, hey, I've been following you on H2O. I was like, oh, great, you should do some competition stuff. I was like, oh, there you are, I see you. And I said, oh, I'm not doing anything interesting. I'm just like pressing the button on driverless. And he goes, me too. So that was all I had. I perfectly ran out of time. So I'd love to talk to you guys afterhand. If you have a question about this, you can definitely find me in the halls or something like that. Sorry we don't have time here, but I'll answer questions until they kick us out of the building. So.
Thanks, Mark.